Hello, so today we are going to do this problem called count good nodes in a binary tree. So the problem says we get a binary tree and a node x in the tree is called good if in the path from the root to that node there are no nodes greater than the value in that node, right? So and the goal of the problem is to return the number of good nodes in the binary tree. So if you take a look at this binary tree here, which nodes are good? So for example, this 3 here, the ones in the path from it to the root, it's only 1 and 1 is smaller than it, so we can put 3. 1 is not, because 3 itself is bigger than 1. So from the root to 1 there is a node with value bigger than 1, so we don't include it. If we take a look here in this path, 3 is smaller than 4 and there is no other thing in between, and so no value is greater than it, and so we include 4. If we go to 5, 4 is smaller than it, 3 is smaller than it, so we include 5. 1 is not included because there is 4 that is bigger than it in the path, right? And so we have 5, 4, 3 and the root itself, right? It's always the case for the root, so it's always at least 1 if there is at least 1 node, and so we return 4, right? Yeah, so that's the problem. Now let's see how we can solve it. Well, of course, like this sounds like a DFS solution, right? Because we want the path from the root to that node, so we can just, as we are doing DFS, keep track of the maximum element we've seen so far, right? So if we keep track of the maximum element and we reach this node, then if it's bigger than the largest we've seen so far in the path, we know all the other elements in the path and the largest one are smaller than it, right? And so we know that that node is good. So the only information we need to pass down to children for each node is the largest in the path we've seen so far. And if we find that this node is bigger than the largest, we can just count it as a good node. So that's the idea. So yeah, let's write that DFS. It should be pretty simple to write. So what we need is just to do a DFS function. And we said we need the node and we need the largest we've seen so far. So let's just keep track of the largest so far. And of course with DFS we need our base case. So we need to return. We don't know yet what we will return. We will check that. So with DFS, to know what you can, if you are unsure of what to return, and that's usually the case initially, you can start out with just a global variable. So I can do that like this, for example, the count. I'll start with a global variable and go from there. So we'll need to call it in the root initially, but what should be the largest so far for the root? Well, since the value has to be smaller or equal, so the values in the path needs to be no greater, so smaller than equal. So for the root itself, let's just pass the root, because for 4, for example, we'll need to check that it's bigger than the root. And so if we pass as the largest value so far the root value, we'll check for 4, we'll check if 3 is smaller than it, and for 1 similar thing, right? And so that's what we need to do here. We need to pass the root val, and then here we return self.count. Okay, so now we need to call on the children, like every DFS. The order here doesn't matter, so we can just start with the normal order. Now, what do we pass as largest so far here? And same thing for the right, what do we pass? Well, if we are going, let's say here, we are at 4 and we want to go to 1 and 5, what should we pass as the largest value? It should be just the largest we've seen so far. But we need to, if 4 is the biggest we've seen so far, like it's this, it is the case here, we need to pass 4 to the call for 1 and pass 4 to the call for 5, because it's the largest so far. And so 5 will just check, am I bigger than 4? Yes, so 5 needs to be counted, and same thing for 1. So here that means we just need to pass the new largest so far, which needs to include the max for whatever we've seen so far, in case there was another number that was bigger. Let's say there was 374, and then we need to take into account this node.val. So let me just do that here, node.val. Okay, and that's what we pass to the left and the right. Now here, how do we need to count, let's say for 4 here, when we visit, for example, when you visit the root, we need to count, and when we visit 4, we need to add 1 to the count, because 4 is bigger than the largest so far, which is 3. And so that means we need to check here if the node value is larger or equal, because the problem says there is no value greater than x. X is the node.val, and so there is no value greater than it. It means it's greater or equal to the largest value we've seen so far. And so we can just say this and increment count if that's the case. Right, so this is basically x bigger than or equal to the largest so far, and largest so far is bigger or equal to all elements in the path to x. And that's exactly what the problem says. The problem says x needs to be, which is node.val, needs to be no nodes with a value greater than x, so which means x is the biggest than all nodes in the path. Right. Okay, so we count, and then we need to, that's pretty much it. We add it to the count, and then we return, and then we return it at the end the count we've seen. We'll restructure this in a moment to not have this global variable, but let's just run this for now and submit. Okay, so that passes test cases. Now to get rid of this self count, we can just have DFS return it, which means here we need to have the count be initialized as 0, add to it here, but we need to add whatever gets returned from the left, right? We need to count it as part of this nodes. So each node will return all the good nodes in its subtree, right? And so that's why we need to return count here. But if we reach a node that is basically the end, what should we return? There are no good nodes there, so we just return 0, right? And that's pretty much it. So let's run this and submit, and that passes test cases as well. Yeah, so that's pretty much it for today's problem. Please like and subscribe, and see you on the next one. Bye.